Hyperbolas. So let's just define them as a set of points. So it's kind of the inverse of an ellipse. It's the set of all points in a plane for whose distances from a set of fixed foci are the difference of those distances is fixed. So on an ellipse, you have the two foci, and the points defined around an ellipse, the sum of their distance is fixed. Here, the difference in their distance is fixed. And the effect that that really has is it almost inverts the ellipse. So basically, the distance between a point on the ellipse and F1, focus 1, and a point on the ellipse and focus 2 will be a fixed constant which is 2a, where a is still the distance between the center and one vertex of the hyperbola. So it's pretty similar to the definition of the ellipse, but the only change is the sum of the distances has become the difference. And in fact, the derivation of the hyperbola is pretty similar as well. So we're not going to go through it. Because the algebra is pretty much the same. You're using the distance formulas, just like we did with an ellipse, and you're simplifying, except that it's going to simplify to x squared over a squared minus y squared over b squared equals 1. So this is the definition of a horizontal hyperbola. And then the relationship between c, a, and b inverts as well. So now c squared equals a squared plus b squared. Versus in the ellipse, it was c squared equals a squared minus b squared. So I'll just go to the blue boxes. Oh, one other thing. Hyperbolas are actually asymptotic. So they have asymptotes. So they're different than parabolas. Parabolas are not asymptotic. They don't approach anything. Their branches don't approach anything. Hyperbolas do. And so I'm going to give you the equations of the asymptotes in terms of a over b. All right. So this is a horizontally opening hyperbola. The way you know it's horizontal is that x comes first. Order matters when you're subtracting, right? So when x comes first, it's horizontal. The size of the denominators doesn't matter in the case of hyperbolas. It's which variable comes first in the difference. That determines whether it's horizontal or vertical. I'm going to show you what I think is an easier way. Rather than memorizing the formula for the asymptotes, when we actually graph one, I'll show you what I think is the easiest way to come up with the equation of the asymptotes. I try and memorize as little as possible. Sometimes it's necessary, but the more space you can keep in your brain just to think about the calculus of the problem and not rote memorization, the better. So then a vertically opening hyperbola will have this equation, right? It'll be y squared over a squared minus x squared over b squared equals 1. Good Lord. Like, that is shaking the camera. Shaking my presentation. All right.
Good.
So A is always the distance between the vertex and the center. That's always A. And we're going to find out that B is the distance between the vertex and what we're going to call the conjugate axis, which is kind of an imaginary axis when it comes to hyperbolas. But I'll talk about that when we do an example. Right here. All right, find the foci and asymptotes of the hyperbola 9x squared minus 16y squared equals 144 and sketch its graph. All right, so they already gave this to us in a kind of a tidy package. We don't have too much work to do to get it into a standard form. All we're going to have to do is divide out the 144. And then I have x squared over, and I can rewrite that as 144 over 9, minus y squared over, and I can write that as 144 over 16, and that equals 1. Well, we saw in our example yesterday, 144 divided by 9 is actually 16. And 144 divided by 16 then is 9. All right. So what's our take? Is this a horizontal hyperbola or a vertical hyperbola? It is horizontal because x is the first variable, right? And order matters in a difference, so it's horizontal. So from this, I can tell that a squared is 16, so a is 4. And I can also tell that b squared is 9, so b is 3. And then we have the relationship that c squared equals a squared plus b squared. And you all remember geometry from like 5 years ago. So that means that we actually have a Pythagorean triple here. C squared equals 3 squared plus 4 squared. What's c?
Cinco.
That's what's up. 3, 4, 5. So c is 5. We have all the information we need to graph, including the foci. All right. So here's what you need to make sure and do. Copy down this graph because sketching a hyperbola is a little bit complicated, but I think this is better than memorizing the formula for the asymptotes. So here's how hyperbolas work. Let's sketch an axis. We know this is horizontal, so A is 4, so I'm going to go out 1, 2, 3, 4. There's my first vertex. 1, 2, 3, 4. There's my second vertex. The foci will be on the same axis as the vertices, right? So the foci are at 5 from my center. So my center in this case is 0, 0. So I just need to go out one more. There's my focus on that side. It's at 5, 0. One more over here. There's my focus on this side. It's at negative 5, 0. All right, so far so good. Now B is the distance to the end of your conjugate axis. So your conjugate axis is an imaginary axis in the opposite direction. So I'm going to go up 3 from my center, and I'm going to go down 3 from my center. Right. And then what I'm going to do is make a rectangle out of my vertices and the endpoints on my what's called my conjugate axis. So we're just going to make a perfect rectangle. So it's like this. No, it's always going to be the center to a vertex. So it depends if it's horizontal or vertical. If it's vertical, the A value is the vertical. But it's always to a vertex. And a vertex is something that's actually on the graph, so not to the conjugate axis. So this is A in this case because it's a horizontal hyperbola. This is B. All right. So our asymptotes go through the center and through the corners of this rectangle. So like this. So all of this stuff that I've shown right now is imaginary. This box is imaginary. It's not actually part of my graph. It's just we're using it to shape my graph. Other than the vertices. I guess the vertices are part of my graph. But now we can pretty easily come up with the equation of the asymptotes if we needed it, if we were asked for it, right? So in this case, the asymptotes are lines. Our y-intercept is 0, so all we need is a slope. And you can see the slope here. What's this coordinate?
Looks like 4, 3.
It's 4, 3, right? It's over 4, up 3. And slope is just rise over run, right? So up 3 over 4. So the slope is 3/4. Meaning the equation of this asymptote is just y equals 3/4 x. Does that make sense? What's the other asymptote?
That negative.
Yeah, it's just the opposite. So if you do it this way, you don't have to memorize the equation of the asymptote. It's pretty easy to just develop it. All right, and now we're ready to actually graph the hyperbola itself. So the hyperbola goes through the vertices, opens around the foci, and trends towards the asymptotes. Does that make sense? So it's just there we go. We found the foci, we found the asymptotes, and we sketched the graph. A little bit more difficult. Oh no, we're going to go right to shifted conics. All we do to shift conics is replace x by x minus h and y by y minus k, and that shifts our center It just shifts the center to HK. So it's not that big of a deal. There's going to be a little bit more attention to detail on finding things like the foci and the vertices, because those are also obviously going to shift with the center. But all it really involves is adding or subtracting something. And you're in Calculus 2, so I'm confident you can add and subtract stuff. All right, so let's attack a few other problems that could be given in different ways. So here, instead of given like a general equation that we have to put in standard form, now we're just given information about the foci and the vertices, and we're asked to write the equation, which isn't too bad. But it does help to kind of sketch yourself a graph of this, just so that you can orient everything and label it. So I'm going to start by just making myself a coordinate plane. All right, so I have vertices. Vertices are always major axis. be that a hyperbola or an ellipse. The vertices are the major on the major axis. So I have vertices at 1, -2, and 5, -2. So 1, and 1, 2. So there's 1, and 2, 3, 4, 5, -2. So right away I know that this ellipse is horizontal, right? The vertices are aligned horizontally. And then my foci are 2, -2, and 4, -2. All right, this one, the numbers are nice enough that I can pretty easily just visually deduce where my center is. Where's my center going to be? It has to be in the middle of all that, right? It's just 3, -2. Does everybody agree with that? Now, if the numbers weren't super nice, you could always just find the center by averaging the vertices, right? So I could do, right, I have vertices that I could do 1 + 5 divided by 2. Well, that's 3. And then if you do -2 + -2 divided by 2, you still get -2. And boom, there's your center, right? All right, but now I know my center. I also know A. A is the distance from my center to one of the vertices. What is that distance? It's 2, so A equals 2. And I also know C. C is the distance from a focus to the center. So what's C? C equals 1. If I know A and I know C, I can figure out B, because in an ellipse, the relationship between A, B, and C is C squared equals A squared minus B squared, right? All right, so for us, 1 squared equals 2 squared minus B squared. So 1 equals 4 minus B. So B equals 3, right? So now I know A, B, and C, and I know the center, which is HK, right? And so the general form of an horizontally opening ellipse will now become this. Instead of just x squared, it's x minus h squared, because it's shifted, over a squared, plus y minus k squared over b squared equals 1. I know h, I know k, I know a, and I know b. All that's left to do is just fill those in, right? So that's x minus 3 squared, over 4. Wait a minute. Oh, that's why. I'm sorry. When I solved for b, I didn't solve for b. I solved for b squared. So this up here is actually b squared, not b. So x minus 3 squared, plus y plus 2 squared over 3 equals 1. Let's just verify this in Desmos. So There we go. That's right where we kind of had our ellipse at in our little sketch. So we're good. Questions about that one? Okay, let's continue. Only a couple more. All right, here's a more standard one. So here we're just given a general form of a conic, and we're asked to find its foci. So sketch it and find its foci. So the way we start a problem like this, first of all, notice both x and y are squared. So what kind of conic does this have to be? It can be one of basically two types if both x and y are squared. Hyperbola or ellipse, right? Can't be a parabola. A parabola only has one of the variables squared. So this is either a hyperbola or an ellipse. First thing we're going to do is group x terms and group y terms. So let's go ahead with that. So I'll say 9x squared. I'm just going to move the minus 72x. And then I'll have minus 4y squared plus 8y. And then I'm going to move the constant to the other side, equals negative 176. All right. So that's step one. Step two, we're going to actually group x terms in parentheses, group y terms in parentheses, and we're going to factor out the leading coefficient on the square term. So for the x terms, I'm pulling out a 9. And I'm going to have x squared minus 8x, and I'm going to leave myself a space there, because what I'm going to be doing is completing the square. Now I know, everybody's afraid to complete the square, because you had a traumatic time with it 4 years ago when you were in Algebra 1 or whatever. I promise it's not as hard as you remember. It's fine. You've done a lot harder stuff. For the y terms, I'm going to factor out the negative 4. I'm going to have y squared plus 2y. I'm going to leave a space to complete the square. And on the right-hand side, I still have the negative 176. Thank you. Be careful. Unlike me, more like Eva. Good, so here's how we complete the square. We're going to do it for x and y separately. I'll start with the x. A general quadratic is written in the form ax squared plus bx plus c, right? So what I want you guys to focus on is what's the b term, and I'm only talking about what's inside the parentheses. So for the x, what's b? Negative 8 divided by 2. Square it. That completes the square. So I'm going to add 16 inside those parentheses. And what we're doing is we're creating a quadratic that's a perfect square. So it's going to factor down to a perfect square. All right, now I can't just add 16. That unbalances the equation. I want to keep it balanced, right? So I'm going to do something to the other side of the equation to balance it. What do I want to add to the other side? Not 16, because am I really just adding 16?
Would it be 16 times 9?
Yeah, 16 times 9 is what I'm adding. So I'm actually going to add 144. And that'll balance it, right? All right, let's do the same thing for the y set of parentheses. What's b? Negative 2 divided by 2 squared. So that completes the square over here. Now, what do I want to put on the other side to balance it? Negative 4. Because I really negative 4 times 1 is negative 4, so I actually took away 4. So it remains balanced this way. All right, so now we're ready to simplify. These both sets of parentheses will now factor down to a perfect binomial squared. On the left here, we'll have 9 times x minus 4 squared. It'll always work out this way, where it's your variable plus whatever b over 2 is squared. In our case, b over 2 is negative 4, so it's just x minus 4 squared. Always works out that way because you built it that way. So minus 4 times, what's the other one going to factor down to? There we go, y minus 1 squared equals negative 36, I believe. All right, so it's either an ellipse or a hyperbola. In standard form, we want them equal to 1, right? So what's the last step? So I'm dividing by negative 36, and what that's going to do, it's going to switch the positions of the x and the y, right? So it's going to make the y term positive and the x term negative. And so what I end up with is y minus 1 squared over 9 minus x minus 1 squared over 4 equals 1. And there's my equation. So there's my hyperbola. Yeah, so y comes first, so this is a vertical, and we are going to sketch this one. First, let's find the foci. So in a hyperbola, the relationship between a, b, and c is c squared equals a squared plus b squared. So just perfect Pythagorean relationship. What's a and what's b? A squared is 9.
Is it 3 and 2?
Yeah,
or is it
a squared is 9, b squared is 4. So a is 3, b is 2. So a squared is 9, b squared is 4. So that's 13. So c is root 13. All right, now I'm going to sketch this out because I think sketching it out as we go will actually help us find the foci. We didn't find the foci here. We found what c is, which will help us find the foci. Let's begin sketching this. All right, where is this hyperbola centered? Careful. Remember, it's x minus h, y minus k, but the center is at hk. Where's 4 coming from? Oh, I wrote it wrong. You wrote it right. Be careful, like Eva. 4-1. If Eva says it and I'm confused, Eva's probably right. 4-1. I agree. Okay. And this is a vertical hyperbola. So the vertices from the center, we're going to go up a distance of a and down a distance of a. So what's a again? 3. So we're going to go up 3 from the center. Oops. So up 1, 2, 3. My center black here. Okay, and then down 3. So down 1, 2, 3. All right. So those are my vertices. The foci should be outside those because we want the branches to wrap around the foci, right? So the foci are going to be on that vertical axis. And C is root 13. So the x-coordinate of both foci will be 4. But the y-coordinate will be the y-coordinate of our center plus root 13. Because C is the distance from the center to a focus, right? All right, what's the y-coordinate of the center? 1. So I should have my first focus should be at 1, comma, or I'm sorry, 4, comma, 1 plus root 13. Well, what's root 13? Little more than 3, little less than 4, right? The square root of 9 is 3, square root of 16 is 4, 13 is in between. So pretty close to 3.5, right? So 1 plus 3.5 is 4.5, so it's just going to be a little bit above 4. Does that make sense? Same deal with the focus down here. It's going to be 4, comma, but now it's going to be 1 minus root 13. So 1 minus 3.5 is like negative 2.5, so just a little bit past that negative 2. Same deal. Does that make sense? Great. Now let's do the conjugate axis. For the conjugate axis, we're going to go, in this case, from the center to the right B units and to the left B units. In our case, B is what? I'm going to go right 1, 2. I'm going to go left 1, 2. It doesn't specifically ask me to label the vertices, so I mean, we could figure out what the coordinates are through, again, just adding and subtracting from the center, but I'm not going to worry about it. We're just going to make our rectangle between the vertices and the endpoints on the conjugate axis. Our asymptotes will go through the center and through the corners of the rectangle. And then our actual hyperbola goes through the vertices and trends towards the asymptotes, wrapping around the foci. One thing I do want to do, I know it doesn't say this, but I just want to show you could still find the equations of the asymptotes, but now it's not just going through, the asymptotes don't just go through the origin, so they are going to have a y-intercept. So I want to talk about how you would figure that out. So you guys are good at algebra. The equation of the asymptotes are just going to be in y equals mx plus b form, right? It's pretty easy to find the slope. Start at your center, and how do I get to the corner of the box? Well, in this case, I'm going up 1, 2, 3, and I'm going over 1, 2. So the slope is 3 halves, right? All right, so y equals 3 halves x plus b. To solve for b, you just need to plug in any other point that that asymptote goes through. Well, we know it goes through the center, and we know that the center is at 4, 1, right? So I'll just plug in 4 for x and 1 for y. So 1 equals 3 halves times 4 plus b. 1 equals 6 plus b. b equals negative 5. So the equation of this asymptote here has to be y equals 3 halves x minus 5. Does that make sense? And you could likewise figure out the equation of the other one. There's the book's drawing, definitely not as good as mine. And that's it. Got some extra time so you guys can work on the problem set today. So here's your part 2 problem set.